Students, the past is where you learn the lesson. The future is where you will apply the lesson. And it is the central or the middle portion of your life which is the most important one. Don't give up in the middle. So keep concentrating hard on your studies. Keep trying hard. Never, 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 ever give up.
Jai Hind Bacho, welcome to my YouTube channel. Uh, Today we are going to start a new topic in the unit light. We will be discussing refraction of light, right? So in today's lecture, we'll be trying to cover these topics. We'll first start with refraction, we'll understand the phenomena of refraction, then we'll discuss the laws. There are two laws of refraction. One is Snells Law and the second one is the normal one. So that we'll discuss, laws of refraction. Then this is very important. We'll discuss about refractive index, its definition, then the factors on which the refractive index of a medium depends. And last but not the least, we will also discuss the rules for bending of light, right? So students, before we start with the actual topic, we need to be aware of certain basic facts. Now look, you all are aware, if light is traveling in a given medium, then it always travels along straight path. This is as per the rectilinear propagation of light. So in a particular medium, light travels along straight path. But when it enters from one medium to another medium, then the path of the light gets bent, right? It deviates. So this bending of light, when light travels from one medium to another, that is actually known as refraction of light. And also students, we all are aware that the velocity of light in air or vacuum is maximum. It is 3 into 10 raised to the power 8 meter per second. But do you know that whenever light enters in a denser medium, in any medium other than air or vacuum, then its speed decreases. So what I mean to say is that the speed of light in different medium is different. So refraction of light can also be stated like it's the phenomena of change in the velocity of the light when light travels from one medium to another medium, right? So let's start with the various technical terms like incident ray, the refracted ray, then the normal, and then we will discuss the phenomena of refraction once again, right? So basically, this is suppose a refracting surface. This can be considered to be a refracting surface. It can be considered to be a refracting glass slab, parallel-sided glass slab. So it can be considered to be a parallel-sided glass slab like this. So this is the point where we need to study the refraction of light, bending of light. So at that point, what to do is you need to draw a normal. Normal, you are aware, it's an imaginary line which is perpendicular to the interface. This line AB, it can be termed as an interface. It may be termed as an interface, right? So the imaginary boundary dividing the two medium, that is known as an interface. Suppose this is medium 1 and suppose this is medium 2, right? And in this case, we'll consider medium 1 to be the rarer medium. Suppose it is the rarer medium, and let us consider this to be the denser medium. Now look, from the term it's pretty clear, denser. The medium in which the atoms or molecules are more closely packed. That is, the medium whose density is more, that is said to be denser medium. While on the other hand, in the medium where the molecules, the constituent particles are much more separated apart from one another, that medium may be termed as a rarer medium, right? For example, between air and water, air is a rarer medium, water is a denser medium. Between water and glass, water will act as the rarer medium, glass will act as the denser medium. Between glass and diamond, diamond is one of the hardest known material. The atoms and molecules are very, very tightly packed. So between glass and diamond, glass will act as rarer medium, Diamond will act as denser medium, right? So, denser medium may also be defined as the medium in which the speed of the light is much more. On the other hand, when the light travels in a denser medium, its speed tends to decrease. The more the denser medium, the smaller will be the speed of the light, right? In that sense, the more the rarer medium, the greater will be the speed of light. So that is the reason why the speed of light in air or vacuum is maximum. So in vacuum, in air or vacuum, the speed of light is represented by c, and it is 3 into 10 raised to the power 8 meter per second. So this is the rarer medium, perfect rarer medium, right? So coming back to this particular topic, look, this is the normal. So what is the normal? Any imaginary line which is perpendicular at a point to the interface, that is known as a normal, right? This AB is interface which separates the two different media. This is medium 1, this is medium 2, right? This is considered to be the rarer medium, this is considered to be the denser medium. So students, in which medium the velocity of light will be maximum? Rarer or denser? It will be the rarer medium where the speed of light is maximum, while in the denser medium it will decrease, right? So, now let us consider an incident ray, and it is incident at point O in an oblique direction. This is an oblique direction. This is normal incidence, this is an oblique direction. So suppose this is the incident ray. Let us consider this to be the incident ray. Now the angle which the incident ray makes to the normal, that is known as angle of incidence. This angle is known as the angle of incidence, right? So the angle which the incident ray makes to the normal is known as angle of incidence. Now student, you are aware light travels along straight path, but while traveling in a single medium, particular medium. So if this glass slab were supposed to be not present over here, then light would have travelled along the same straight path. So this is basically the incident ray when produced. If the glass slab is considered to be absent, then the ray would have travelled along the same straight path, right? But now since after point O, the light enters another medium and it enters denser medium, it travels from rarer to denser medium. So what happens? Bending of the path of light takes place. So in this case, it tends to bend towards the normal. It tends to bend towards the normal. This ray is known as the refracted ray. This ray is known as the refracted ray. And the angle which this refracted ray makes to the normal, it is known as the angle of refraction. This angle. This is known as the angle of refraction. Right? Again, I must convince you once again. Look, in case of a single medium, if the glass were assumed to be absent, then light would have travelled along the same straight path. Because in a given medium, light always travels along the same straight path. But here, light is travelling from one medium to another medium, from rarer to denser. So light tends to bend towards the normal. I'll explain the reason behind this, right? So light is bending towards the normal. This is the incident ray, this is the refracted ray. And if it emerges out of the slab, then that will be the transmitted or emergent ray. Anyway, we'll discuss it later on. But the angle which the incident ray makes to the normal, that is angle of incidence. The angle which the refracted ray makes to the normal, that is angle of refraction. Now here one thing is clear. Since the ray is bending, refracted ray is bending towards the normal, therefore angle of refraction is less than the angle of incidence. Right? So what we have discussed is, whenever light travels from one medium to some other medium, then the path of the light bends. And student, this phenomena of bending of light, when it travels from one medium to another, is known as refraction of light. Is it clear? This is in terms of bending of light. Now, refraction of light can alternatively be stated in terms of the speed of light in the two mediums as well. Now look, suppose this medium is air or vacuum, and this medium is any denser medium, suppose it is glass. So as I stated, the velocity of light in air or vacuum is maximum and it is represented by c. So when the light travels in air or vacuum till this point, its speed will be c. As soon as it enters the glass, which is a denser medium, its velocity tends to decrease. Its velocity tends to decrease. So your v is less than c. C would be always maximum. It's the speed of light in air or vacuum. As I told you, the more the denser the medium is, the lesser will be the speed of the light in that particular medium. So, speed of light in air or vacuum is maximum. And whenever light enters in some denser medium, its speed tends to decrease. So, whenever light travels from one medium to another, the speed of the light also gets changed. So, students, refraction of light is the phenomena of change in the velocity of light whenever light travels from one medium to some other medium, right? So this is how refraction of light can be defined. Again, I'll repeat the key points. First is, light travels along straight path when it is traveling in a given medium, in a single medium, in a given particular medium, then light always travels along straight path. Second point, whenever light enters from one medium to another medium, then the path of the light bends. It either bends towards the normal or it bends away from the normal. We'll discuss both the cases later on, right? Third, the speed of light in different medium is different. So what happens is, whenever the light travels from one medium to another medium, then there is a change in the velocity of the light. So students, the phenomena of bending of light or the phenomena of change in the velocity of the light whenever light travels from one medium to another medium, that is known as refraction of light. So I hope you have understood the definition of refraction of light, right? So let's proceed further. We have also discussed some technical terms: normal, incident ray, refracted ray, angle of incidence, angle of refraction. Understood? So these are the technical terms involved. AB, that being an interface. Now let's discuss laws of refraction. So there are two laws. First law. It is also known as Snell's Law. It is also known as Snell's Law. This law can be mathematically verified as well. Now look, the statement of Snell's Law. This angle of incidence, R is the angle of refraction. So the ratio of sin I and sin I, this is the trigonometric function sin divided by sine of angle of refraction is found to be constant. So this is basically Snell's law, which is the first law of refraction. So what will be the statement? According to Snell's law, it states that the ratio of sine of angle of incidence to the sine of angle of refraction is always constant. And student, this constant is known as refractive index. It is known as refractive index of the medium. It is known as refractive index of the medium. We'll discuss about this term in detail in the next topic, right? And I'll represent it by this symbol, mu. This may be used to denote refractive index, or even make use of notation n as well. It's your wish. So here I will represent refractive index by mu. This is mu. So this will represent refractive index, right? So the statement for the first law is the ratio of the sine of angle of incidence to the sine of angle of refraction is constant, and that constant is equal to the refractive index of the medium, right? So we are considering two mediums. So refractive index of one medium with respect to other, that we'll discuss in the later topic. So let's first discuss the laws. And second, now look, here this is the incident ray, this is the refracted ray, and this is normal. All these are lying on the board of, on the plane of this whiteboard, isn't it? So that's second law. Second law states that the incident ray, the refracted ray, and the normal to the interface all lie in the same plane. So these two are collectively known as the laws of refraction. Right? So first law is Snell's law, which is sin I by sin r is equal to constant, which in turn is equal to the refractive index of the medium. And second is the incident ray, the refracted ray and the normal at a point to the interface all lie in the same plane. So these two collectively are known as laws of refraction. So this is also laws of refraction. Now let's come across this very important topic of refractive index, right? So let's discuss about refractive index. Student, we will discuss refractive index both in terms of the velocity of light as well as in terms of the wavelength, right? So let's start with the definition first. Definition of refractive index. Actually, if you consider this to be air or vacuum and this to be a denser medium, then it is known as the absolute refractive index, right? So, absolute refractive index. It is the refractive index of the medium with respect to air or vacuum. That is known as absolute refractive index. Like glass placed in air or vacuum. We are considering the medium water with respect to air or vacuum. We are considering diamond with respect to air or vacuum. So whenever a medium is placed in the surrounding medium which is air or vacuum, then the refractive index of the medium under consideration is known as absolute refractive index. And students, it is denoted by, or it is rather defined as, the velocity of light in air or vacuum divided by velocity of light in that particular medium, in the medium. So, refractive index, I am talking about the absolute refractive index. It is defined as the ratio of velocity of light in air or vacuum, which is represented by small letter c, to the velocity of light in that particular medium. Let's consider this case. This is glass, this is a glass slab which is placed in air or vacuum, right? So this will be glass with respect to air or vacuum, with respect to air or vacuum. It is known as absolute refractive index. Again repeat, whenever we are dealing with the refractive index of a medium with respect to air or vacuum, that is, if the medium is placed in a surrounding medium which is air or vacuum, then the refractive index must be absolute refractive index. Now while travelling in air or vacuum, the speed of light is c, and whenever it enters the medium, denser medium, its velocity will get reduced to v. So the ratio of c by v is known as the absolute refractive index. Now as we can notice, it is the ratio of two similar physical quantities. This is also velocity, denominator is also velocity. So it must be having no unit at all. So refractive index being the ratio of two similar physical quantities do not possess any unit. So refractive index in terms of velocity of light is defined as the ratio of the velocity of the light in air or vacuum to the velocity of light in that particular medium. Clear? So one more thing. Since c is greater than v, velocity of light in air or vacuum is maximum, which implies that c by v is greater than 1. Therefore, absolute refractive index, that is the refractive index of medium with respect to air or vacuum, it is always greater than 1. Students, the value of absolute refractive index of a medium is always greater than 1. It is always greater than 1. I'll give you some example. Like the absolute refractive index of water, it is 4 by 3. It is 1.33. When I say absolute refractive index of water, what I mean to say is that refractive index of water with respect to air or vacuum. Clear? That's the meaning of absolute refractive index. One of the two mediums must be air or vacuum. Then it will be the absolute refractive index. Absolute refractive index of glass. There are various types of glass, crown glass, print glass, but normally the absolute refractive index of glass is 3 by 2. That is 1.5. Again, absolute refractive index of glass means refractive index of glass with respect to air or vacuum. Refractive index of diamond. Diamond is one of the hardest known material. It is 2.4. So what I mean to say is that, please mark my words, the absolute refractive index of a medium is always greater than 1. These are few examples. The greater the absolute refractive index of a medium, the greater will be its density, and the lesser will be the speed of light in that particular medium. Clear, students? These are some basic concepts which being a science student you must be aware of, which you need to know. So this is regarding the absolute refractive index. Now this absolute refractive index, it may also be defined in terms of the wavelength. We all are aware of this particular formula, isn't it? We know that velocity is equal to frequency multiplied by wavelength. We all are aware of this particular formula. So velocity, in case of air, C, it is nu into lambda. Lambda stands for wavelength. As we are aware, frequency, it indicates the energy, right, of the radiation. E equals to h nu. So basically energy remains constant, isn't it? Energy is conserved. So what I mean to say is that even when light travels from one medium to another medium, it is the frequency which remains constant. So frequency of the incident ray or the frequency of the refracted ray, it will remain same. But the velocity as well as the wavelength, it will get changed. It will get changed. Suppose it is air and wavelength will get changed. Here the wavelength of light may be considered to be lambda medium. So students, do remember, during refraction when the light travels from one medium to another medium, it is the energy of the radiation which will remain conserved, and energy is proportional to frequency of the radiation. So frequency of light, whether it travels in one medium or the other medium, it will remain constant. It doesn't change. So even when light travels from one medium to another during refraction, frequency remains constant. It is the velocity and the wavelength of the light that get changed when it travels from one medium to another medium. So what we do is, let us now define refractive index in terms of wavelength, right? So what we do, let's make use of the formula which we have just now discussed. Look, refractive index, it is defined as the ratio of this velocity of light in air or vacuum to the velocity of light in that particular medium. Now C is nu into lambda, air or vacuum. This is the formula. Velocity is frequency of the light multiplied by wavelength of the light. This is again the velocity of the light in that particular medium. So in the medium the frequency will remain same, but the wavelength will get changed. So lambda medium. So therefore absolute refractive index may also be defined as lambda air divided by lambda medium. So in terms of wavelength, refractive index may also be defined in this particular manner. So student, absolute refractive index of a medium may also be defined as the ratio of the wavelength of the light in air to the wavelength of the light in that particular medium. So this is how the refractive index can be defined, right? So again, let me repeat this topic. Refractive index is the characteristic of a given medium. It basically represents how dense a medium is, right? And it also depends upon the nature of the surrounding medium as well. That also we will discuss. So refractive index represents the density of the medium under consideration. More denser the medium is, more will be the refractive index of that particular medium. So students, if I say absolute refractive index, it means that refractive index of a given medium with respect to air or vacuum. So it can be defined in two ways. In terms of speed of light, absolute refractive index is defined as the ratio of the speed of light in air or vacuum to the speed of light in that particular medium. In terms of wavelength, absolute refractive index may be defined as the ratio of the wavelength of the light in air to the wavelength of the light in that particular medium. And refractive index being the ratio to similar physical quantities, it will have no unit. And also remember students, the absolute refractive index of any medium must be greater than 1. It must be always greater than unity. I hope it's absolutely clear. Now let's come across the relative refractive index. Now let us consider the case of relative refractive index. So for that, what to do is, suppose we consider two mediums, 1 and 2. And one medium can be considered to be water, the other medium can be considered to be glass. We are not considering air or vacuum, right? So let's consider these two medium. This is suppose medium 1 and this is suppose medium 2. Let us consider this to be water and this to be glass. So water will act as a rarer medium, glass will act as a denser medium, right? So what happens is, when the ray travels from rarer to denser, it will bend towards the normal like this. This is the angle of incidence, this is the angle of refraction, right? Here the speed of light is suppose v1. Here the speed of light is suppose v2. Obviously in the rarer medium, the speed of light is greater than that in the denser medium, right? So here the refractive index of medium 2 with respect to medium 1, this is how it is written, and it is read as refractive index of medium 2 with respect to medium 1. Always remember, just check the medium in which the angular refraction lies. Here the angular refraction lies in the second medium. So it will be refractive index of second medium with respect to the first medium. So here both the mediums 2 and 1, right? There is no air or vacuum involved. So in this case it is known as relative refractive index. Means refractive index of medium 2 with respect to medium 1. That is known as relative refractive index. And it is defined as the ratio of velocity of light in the first medium to the velocity of light in the second medium. So in terms of the relative refractive index, it is written as V1 by V2, right? So again I repeat, suppose light is traveling from medium 1 to medium 2 and angular refraction lies in medium 2. Then the relative refractive index is written as mu21, which is read as refractive index of medium 2 with respect to medium 1. It will be defined as the ratio of the speed of light in medium 1 to the speed of light in medium 2. Right? So in case we consider it to be water, we consider it to be glass, then it would have been refractive index of glass with respect to water. It would be equal to speed of light in water divided by speed of light in glass. Now it is again represented by mu into lambda water divided by mu lambda glass. So relative refractive index of glass with respect to water, it would be equal in terms of wavelength lambda water divided by lambda glass. So this is the proper way of representing relative refractive index. So students, out of the two medium, if you consider one to be air or vacuum, then it would be the absolute refractive index. And other than air or vacuum, if you consider other two mediums like water, glass, diamond, any other liquid, glass, then it would be the case of relative refractive index. Refractive index of different medium is different. Students, look, density of different medium is different, So refractive index does depend upon the density, does depend upon the nature of the medium. The more denser the medium is, the more is the refractive index of that particular medium under consideration. So factors on which refractive index depends. So first one is, it depends upon, refractive index of a medium depends upon the nature of the medium. It depends upon the nature of the medium. Different medium will possess different refractive index. So it does depend upon the nature of the medium. Not only this, student, it will also depend upon the nature of the surrounding medium in which this medium is placed. So it depends upon the nature of surrounding medium. What I mean to say is that, suppose this is a glass slab placed in air. So refractive index of glass with respect to air, it is 1.5, right? Suppose this is glass, it is placed in water or some other medium. In this case, refractive index of glass with respect to water would be different. It would be different. And that can be evaluated. So what I mean to say is that not only refractive index depends upon the nature of the medium, but it also depends upon the nature of the surrounding medium in which it is placed. Or collectively, you can combine these 2 points. You can state that refractive index depends upon the nature of the pair of the two media. Nature of the pair of the two media. Right? The actual medium whose refractive index is to be determined and the medium in which the first medium is to be placed. So it depends upon the nature of both the medium. Third, it depends upon the wavelength. It depends upon the wavelength of the light. It depends upon the wavelength. Look, there is a relation known as Cauchy's relation. It relates the refractive index of a medium with the wavelength. The formula is A plus B by lambda square plus C by lambda 4. This is known as Cauchy's relationship. Now, with the reference of this particular relation, we can easily conclude a basic fact. The greater or the longer the wavelength of a given radiation, the smaller will be the refractive index of the medium for that particular wavelength. So what I mean is, a given medium will have different values of refractive indices for different wavelengths or for different colors. Different wavelengths means different colors. Right? I'll explain it in detail. Students, you all are aware of the constant colors of white light. It is vibgyor, violet, indigo, blue, green, yellow, orange, red. So when white light splits into its 7 constant colors, that is vibgyor, V-I-B-G-Y-O-R, vibgyor. Wavelength of red is maximum and violet is minimum. This is known as visible spectrum. It is known as visible spectrum. And wavelength for violet is minimum and wavelength for red is maximum. So make use of this. Wavelength of red radiation or red wavelength is greater than wavelength of violet. Therefore, using this relationship, what do you get? Refractive index of the medium for the red color would be less than the refractive index of the medium for the violet color. Understood now? So what I mean to say is that same medium, I think a glass slab, when different wavelengths are incident, monochromatic beam are incident, red light, then orange, then blue, then violet, green, the same medium, which is glass in this case, will have different values of refractive index for different colors, for different wavelengths. The refractive index of glass for red radiation would be minimum. The refractive index of glass for violet radiation, violet color would be maximum. That is what I mean to say. So refractive index depends upon the color of the radiation. That is, it depends upon the wavelength of the radiation. Understood? So students, these are the 3 factors on which the refractive index depends. Again, I must repeat it. Refractive index of a medium depends upon its nature, depends upon its own nature. Second, it depends upon the nature of the surrounding medium in which it is placed. Third, refractive index of a medium for different wavelengths, for different colors is found to be different. So from there we can conclude that refractive index of a medium does depend upon color of the radiation, does depend upon the wavelength of the radiation. For red radiation, the refractive index of a given medium would be minimum. For violet radiation, the refractive index of a given medium will be maximum. Right? So these are the three factors on which the refractive index of a medium depends. Now students, after finishing the topic of factors on which the refractive index depends, let's discuss the other one. Rules of bending of light. We have done this as well. So now let's discuss rules of bending of light. So, let's consider rule 1. Suppose this is the interface. This is medium 1, this is medium 2. This is suppose rarer medium, and let us consider this to be denser medium. Right? So, this is the normal. At this point, we need to study refraction. So, light is to be incident at point 2 in an oblique direction. This is the oblique direction. This is the incident ray. The angle which the incident ray makes to the normal would be the angle of incidence. This is the angle of incidence. Now look, if medium 2 is considered to be absent, then light, as per the rectilinear proportional light, would have travelled along the same straight path. But here, since light is travelling from one medium to another, that is from rarer to denser, it bends. And in this case, it will bend towards the normal. The light will bend towards the normal. This is the normal. This is the normal. So it will bend towards the normal. And the angle which the refracted ray makes with the normal, it is known as angle of refraction. So from the diagram, it is pretty clear that angle of refraction is less than the angle of incidence. We can easily verify this. Let's try to verify, right? So this is rarer medium. Suppose here the speed of light is v1, and in the denser medium the speed of light is v2. Students, I have told you a very basic fact. Speed of light in rarer medium is always greater than the speed of light in the denser medium. So what I mean to say is that v1 is greater than v2, right? v1 is greater than v2. Therefore, v1 by v2 would be greater than 1, right? Also, v1 by v2 is equal to refractive index of the second medium with respect to first medium, like this. And refractive index is given by sin I divided by sin I. As I told you, it is read as refractive index of medium 2 with respect to medium 1. Right? It is to be considered in which medium the angular refraction lies. If the angular refraction lies in the second medium, then on applying Snells Law at point 2, we will write refractive index of medium 2 with respect to medium 1. Now look, it implies that sin I is greater than sin R, which further implies that angle I is greater than angle R. So it's verified, angle I is greater than angle R. So students, rule number 1, whenever light travels from rarer medium to denser medium, then the refracted ray tends to bend towards the normal. Or in other words, the angle of refraction in the denser medium is less than the angle of incidence in the rarer medium. So that's rule number 1, and this is the mathematical verification of it, right? Okay. Rule 2. Now what to do is, let's interchange the medium. Suppose in this case, this is medium 2, or rather, suppose it's considered to be the denser medium, and let us consider this to be the rarer medium. Let's consider this to be the interface AB. This is the point where the refraction is to be studied. So what to do? The first step is to draw a normal. Normal is any imagined line which is perpendicular to the interface. This is the normal. Then light needs to get incident at point O in an oblique direction, not normal direction, in an oblique direction like this. This is the incident ray. The angle which the incident ray makes with the normal, that's angle of incidence. In this case, the light is traveling from denser to rarer. So in such a case, when light travels from denser medium to rarer medium, the ray bends away from the normal. In the absence of the medium, it would have traveled along the same straight path. But in this case, light is traveling from denser to rarer. It will bend away from the normal. So this is the refracted ray. This is the angle which it makes with the normal. So here, this is the angle of refraction. So it's pretty evident over here, angle of refraction in the rarer medium is greater than the angle of incidence in the denser medium. Right, students? It's simply the vice versa of rule 1. Rule 1 is rarer to denser, the refracted ray tends to bend towards the normal. Denser to rarer, the refracted ray tends to bend away from the normal. In this case, when the light is traveling from rarer to denser, the angle of refraction is less than the angle of incidence. In this case, when the ray of light is traveling from denser to rarer, the angle of refraction is greater than the angle of incidence. Right? Here also you can easily justify. I mean, over here it is V1 and suppose it is V2. In this case, which velocity will be greater? V2. Students always remember, speed of light in rarer medium is always greater. In the denser medium it is always less. So this is considered to be rarer. I have interchanged the medium, isn't it? Now this is rarer and this is denser. So there V2 is greater than V1. Right? So therefore V1 by V2 would be less than 1. Earlier it was greater than 1. In this case it would be less than 1. So refractive index would be less than 1 and therefore sin I divided by sin R would be less than 1, which implies that sin I is less than sin R, which further implies that angle I is less than angle R. So it's mathematically verified. So in this case, when the light travels from denser medium to rarer medium, the angle of refraction is greater than the angle of incidence. Right? There is third one as well. It's not a rule, but do remember it. This is suppose the interface and this is the point. And there is a normal over here. This is suppose medium 1 and this is suppose medium 2. It is an oblique direction. Now what happens when the ray of light is incident normally? This is the incident ray. So this is known as normal incidence. It is known as normal. Normal means 90 degree for normal incidence. So what is the angle which the incident ray makes with the normal? Yes students, what is the angle which the incident ray makes with the normal? It's not 90 degree, it is 0 degree. Normal and this is the incident ray. Both are coinciding. So the angle which the incident ray makes with the normal is 0 degree. So angle of incidence is 0. So here angle of refraction is 0. So it will remain undeviated. So what I need to say is that, again, a very, very important concept. When ray of light is incident normally on a transparent refracting medium, then the ray of light won't get deviated. It will remain undeviated. So in this case, there is no bending of light, no refraction takes place. Refraction takes place only when ray of light get incident in an oblique direction other than 0 degree, right? In an oblique direction. Then only it tends to get bent either towards the normal or away from the normal. So in the third scenario, when the ray of light gets incident normally means making an angle of 0 degree with the normal, that is angle of incidence is 0. So in that case angle of refraction also becomes 0. So in that case the ray of light remain undeviated. So no refraction whatsoever will take place in this case. So student, I hope you have understood this concept. This was a very, very important concept. So we have discussed all these 5. refraction, laws of refraction, refractive index, factors on which the refractive index depends, and obviously rules of bending of light. Right? We'll discuss some another very important concept. We can discuss the principle of reversibility of light. Also students, you need to understand to apply Snell's law. That also I will tell you, and after that we can discuss the principle of reversibility of light. Right? Let's consider 2-3 cases. Right? Case 1. This is medium 1, this is medium 2. Indication of this arrowhead is very, very important. Suppose this is rarer medium, and let us consider this to be denser medium. So obviously it will bend towards the normal. This will be the angle of incidence. This will be the angle of refraction. Isn't it? And this is the normal. This is the normal. So at point O, if you apply Snell's law. Now in this present scenario, I am trying to convince you how to apply Snell's law, right? If you apply Snell's law over here, it will be ratio of sine of angle of incidence to the sine of angle of refraction. It is equal to refractive index. Now refractive index of which medium with respect to which medium? Right? That is to be understood. For that, simply remember my wordings. You need to check that in which medium the angle of refraction lies. In this case, the angle of refraction lies in the second medium. So, it will be refractive index of medium 2 with respect to medium 1. Again, I must tell you, during the refraction, just check in which medium the angle of refraction lies. So, applying Snell's law, you will write sin I over sin r is equal to refractive index of the medium in which angle of refraction lies with respect to the medium in which incident ray travels. So that is how Snell's law is written. Clear? For example, this is glass and this is suppose water. This is water and this is glass. Let's consider this another example. This is the normal over here. This is the incident ray. Indicate the arrow. So this will be the angle of incidence. So out of glass and water, obviously glass is a denser medium and water is a rarer medium. So light is traveling from denser to rarer. It will bend away from the normal. So it will be like this. It will bend away from the normal. So this is angle of refraction. So now if we apply Snell's law at point O, what we get is sin I divided by sin r. Students, look, here angle of refraction is lying on water. So it will be refractive index of water with respect to the medium in which incident ray is traveling, that is glass. So this is how Snell's law is applied. Again I repeat, you need to check the medium in which angle of refraction lies. So the refractive index would be the medium in which the angle of refractive index lies with respect to the medium in which the incident ray is traveling. Right? This is how the Snell's law is applicable, or this is how the Snell's law is mathematically expressed. Right? So, let's deal with the principle of reversibility of light. So, let us discuss this. Principle of reversibility of light. It's a very, very simple concept actually. Now look, let's consider this to be an interface. This is suppose medium 1. It's considered to be the rarer medium. Let us consider this to be medium 2. It's considered to be a denser medium. Right? This is a denser medium. Water or any other medium. What we do is, suppose we draw normal over here and ray of light is incident like this. So this will be the angle of incidence, right? Ray of light is traveling from rarer to denser, so it will bend towards the normal. This will be the angle of refraction, no doubt regarding this. And here, suppose a plane mirror is placed. Here, suppose a plane mirror is placed. This is a plane mirror. This is suppose a plane mirror. And the light gets incident normally over here. It is getting incident normally over here. So this, students, we have already discussed in reflection of light. When light gets incident normally on a plane mirror, then what happens? It will get reflected back and it will retrace its path in the opposite direction. So this is path 1. This is path 1. Like this. This is path 1. And after getting reflected, here angle of incidence is 0 and angle of reflection is also 0. So it will get reflected back. This is path 2. This is path 2. This is path 1. And on getting reflected, it will retrace its path in the opposite direction. This is path 2. Right? So what to do is, we will apply Snell's law for path 1 as well as for path 2. And we will come across a very, very important result. Again, I repeat, students, we are discussing the principle of reversibility of light. So what you consider is there is an interface separating two different media. This comes to be rarer and this comes to be denser. Right? Let this be water, this be air. So when light gets incident in an oblique direction, and if it is traveling from rarer to denser, it will bend towards the normal like this. Now suppose a plane mirror is placed in such a manner that this ray get incident normally on the plane mirror. Normally on the plane mirror means angle of incidence will become 0. So the angle of reflection will also become 0. So after getting reflected, this is path 2. It will retrace its path in the opposite direction. Fine. So light is made to reverse its direction after getting reflected from this mirror. So for path 1, let's apply Snell's law. What do you get? Sin I divided by sin I. Ratio of sine of angle of incidence to the sine of angle of refraction is constant, and that is refractive index. Now students, how to write this refractive index? Again I must repeat. Angle of refraction is lying in the medium 2 and incident ray is travelling in medium 1. I am considering path 1. So it will be refractive index of which medium? Of the medium in which angle of refraction lies. With respect to which medium? In which the incident ray travels. So this will be the first equation. Clear? Now apply Snell's law for path 2. We are dealing with this particular path when it is retracing in its opposite direction. So again apply Snell's law at point 2. Now when the light travels along this path, so this will be the incident ray and this will be the refracted ray. This will be the angle of incidence, this will be the angle of refraction. Right? I am dealing with this particular path, path 2. So this is incident ray, this is refracted ray. So in this case, sine of angle of incidence divided by sine of angle of refraction. This is the angle of incidence, this is the angle of refraction. It will be equal to refractive index of, for path 2, this is the angle of refraction. So it lies in medium 1. So it will be refractive index of medium 1 with respect to medium 2. Clear? So what we have done is, we have obtained two equations by using Snell's law. One is for path 1 and the second one is for path 2. Now multiply these two. Multiply these two equations. What you get is sin I divided by sin I multiplied by sin I divided by sin I. It will be equal to mu 2 1 multiplied by mu 1 2. So it is 1 mu 2 1 multiplied by mu 1 2. So we get a very, very important result. So mu 2 1 is equal to reciprocal of mu 1 2. This is a very, very important concept. Right? So refractive index of medium 2 with respect to medium 1 is equal to reciprocal of refractive index of medium 1 with respect to medium 2. I'll give you some examples so as to clear the concepts. So basically, what's the principle? What's the statement then? The principle of reversibility of light states that if the light is made to suffer any number of reflections and refractions, and if its final path is made to retrace, if it is reversed, then it will retrace its path in the opposite direction, following the same path but in the opposite direction. And this is basically the consequence of principle of reversibility of light. Right? So what is the statement of principle of reversibility of light? If the light, after suffering any number of reflections or refractions, has its final path reversed, then it tends to retrace its path in the opposite direction. That is what we have discussed over here. And this is the consequence of principle of reversibility of light. Now, refractive index of glass with respect to air. This is absolute refractive. It is 3/2. So, what will be the refractive index of air with respect to glass? It will be reciprocal of this. Just now we have discussed. So, it will be equal to 2/3.
So students, that's it for this particular session. I hope you have understood all the concepts which have been taught to you in this particular episode. So do join me in my next lecture then. Till then, goodbye and do take very good care of yourself. And do like, share and comment. Thank you.